Hello everyone and welcome to part 4 of a To Be Astronomer reacts to the Flat Earthers alternative to gravity, also known as Incoherent Electrostatic Acceleration. Alright, let's just get on with it.
Medium we live in. Gases have different electric potentials, just like all matter does.
Yes, kind
The
of.
gas molecules that can hold more potential than those gas.
Well, I don't like the phrasing here, right? I wouldn't say they hold electric potential, I'd say they have electric potential. This might seem like a small difference right there, but electric potential is essentially the amount of work that is necessary to move electric charges around, right? Yeah, and work is essentially energy, right? So potential and electric. So potential and energy are related to each other, right? Electric potential, the unit for that is actually volt. This is something that you probably can work with. And voltage is the way we learned it in university, is essentially defined as the difference in electric potential, right? So if you have some object that is charged with charge A and has an electric potential of A, and then you have another object whose electric potential is not A, you gotta have a voltage between them, right? That's essentially, because it's a potential difference, really.
Molecules around them are theoretically more dense and will have a stronger attraction
It
towards
has
the negative.
nothing to do with density. It's charge density. Charge density. That's important. Not density, charge density.
Ground below.
Also, wait. The article he shows here is essentially a paper on gas that is influenced by external and internal electric fields. Now, it might not seem that way, but astronomers actually think a lot or do a lot of things with gases that are influenced by external and internal electric or mostly magnetic fields, because this might, we believe that this is rather relevant in the formation of stars and in the collapse of clouds, right? That there are external and internal electric and magnetic fields that do stuff. And one of the things that they also taught us at university is so-called charge shielding, that if you have a sufficiently large amount of oppositely charged particles, they shield each other, right? Because their respective electric fields, they really are kind of quenched by all of the other opposite charge. So you're not helping yourselves there, because most bulk matter is for practical purposes neutral, and it's neutral because it has a positive nucleus and a negative hull. So the shell of the atom is negative and the nucleus is positive, because there are protons in the nucleus and electrons in the shell. So bulk matter is neutral. That's essentially what we know already, right? And it is not enough to create I mean, most certainly there are extremely small, tiny electromagnetic forces at play, but those are not big enough, even by a long shot, to create the gravity that we feel. So there needs to be another explanation for it, and that's mass, but that's not the flat earthers' conclusion, of course. And what I mean by those small electromagnetic forces are too small by a long shot is I'm talking about bulk matter, about scales that are by far larger than typical atomical scales, right? Because on an atomic level, of course, the electromagnetic forces and then like on molecular levels, those play a huge role, but not on the scales that we operate at.
Theoretically more dense and will have a stronger attraction towards the negative ground below.
Well, if the charge density is high, the net charge density, that would work, but it's not, so it doesn't.
When these gases are carried along the downward vector by
I also like how it just says vector. No, not a vector of something. It's just a vector, you know. I guess what he's trying to say is that here there's an electric potential that is pointing downwards, right? That I believe is what he's trying to say. This ties in with the voltage thing he has shown earlier, and he says that because matter has charge carriers inside of it, it will follow this voltage. It is moved down by the voltage, right? That is his explanation. There is so much wrong with that explanation. So much. How would that work if you are in a car? I mentioned that earlier. Shouldn't the downward vector be absolutely minute inside a car? It should. It definitely should be. But you know, that's they. I don't think they thought about that, and I also think that their reply would just be, "But a car is also charged," and that's just it. But yeah.
By these electrostatic.
Cars are for practical purposes are Faraday cages, and you don't even need a car. You can take something that's a lot more minute, but put a long enough stick of rebar in the ground, and suddenly, you know, it would stick out. Imagine you have a stick and you stick it like a piece of rebar, and you stick it in the ground and it's like 10 meters high. Shouldn't this also be then a negative pole, and things should randomly be attracted towards this pole of rebar? Completely ridiculous.
Forces, the lighter gas gets displaced and becomes buoyant.
No, gases, even though, of course, the air has a positive charge, that you can, you know, if there's a particularly dry day, and sometimes it's enough when there's a dry day and humidity is low and things like that, and you get zapped when you touch metal objects. I know that because in the office I work in at university, I always get a zap when I touch any of the appliances or the coffee machine, even the toaster in rare occasions. And this is because the Earth is on, like, the Earth is negatively charged and the air is slightly positively charged, right? And so that's what creates that. However, the charge rates inside the atmosphere between the different molecules, I must admit I don't know. I'd imagine that nitrogen and oxygen are more easily charged than the other gases. Hydrogen, however, should be somewhat easily charged too. So, but the key thing here is that this doesn't explain the what do you call it, this layering of the gases, right? Because if you only have charged hydrogen, which is just a proton, one charged proton would have a better charge to mass ratio than a charged oxygen, because both of them are going to be charged, like carry +1 charge, right? And the one with the higher charge to mass ratio would be pulled down, because mass acts as inertia. So hydrogen should be on the bottom, not oxygen. So that's completely the wrong way. Even your own theory disagrees with you there. I love it.
Until it finds a place with the same electrostatic potential. This is why we have a pressure density gradient.
I just explained how that's wrong. Also, hydrogen, like again, hydrogen would be on the bottom, and the heavier ones would be on the top, unless they're multiply charged, right? If you have an oxygen that's charged twice, I mean, the charge to mass ratio would still be a lot worse than hydrogen, but that way you could get it further down in their model. It's still wrong. Also, how come the pressure dependency with height can be calculated only using gravity and thermodynamics? I will show that in another video. It's actually called the scale height. That's a really simple thing in atmospheric physics, and sometimes we use it in astronomy too. The scale height for Earth is about 7 point something kilometers. There you go. The scale height. The scale height. So the thing I wanted to say is that the scale height you can very, very easily calculate. The scale height is the height at which the pressure has dropped by a factor of E, right? And just look at the Wikipedia page for its derivation. Essentially, the only thing you need is K times the temperature, K being the Boltzmann constant, divided by the molecular mass of whatever you have in the air and the acceleration due to gravity, by the way. That gives you the scale height perfectly. So for atmospherical processes, unless we're talking inside a thunderstorm or similar, electromagnetic forces can be neglected pretty much entirely. And that's right here is the barometric pressure formula, where I can calculate the pressure at a given height. And this works for the entire atmosphere, right? You have minus Z, where Z is the height divided by the scale height H. And you have that in an exponent and the starting pressure, if you will, at 0. And this works so remarkably perfect, right? It is used everywhere. Essentially, every time you need a pressure reading, you use this formula, and it works so nearly flawlessly. The only thing it is influenced by is local pressure differences due to weather, right? You have probably seen those weather diagrams where they have a low pressure and a high pressure system. That's the only real derivation you have from that. And this only uses classical gravity and thermodynamics. None of the two take into account this charge. I'm sorry, the recording randomly closed there. I don't know what happened. What I was saying, if you have these explanations already, there's absolutely no need to come up with the electrostatic acceleration. Also, you have not been able in any way as of yet to quantify this incoherent electrostatic acceleration. Why don't you give us the charge numbers of Earth and the atmosphere so I can do calculations with them? That's probably the reason, because then I could do calculations with them.
And are told the noble gases work their way up into the higher
We're not told that the noble gases make their way up. Hydrogen is not a noble gas. Hydrogen very much is a reactive gas. That's, helium is a noble gas, that's true. Helium is very far up. You see, the issue here is that noble gases don't travel up. It solely and only depends on the molecular mass that each of these molecules have. In helium, it's just a single atom, right? Because helium is very non-reactive. It's just one Ag traveling up. And for hydrogen, which is not a noble gas, it's H2, right, that is traveling up. The next noble gas would be neon. Neon is not the amount of neon that we have on Earth is rather small. Argon then is another one that we have quite a bit of, right? And argon isn't up. Argon is definitely more heavy than helium. I don't know if it's heavier than nitrogen off the top of my head, but I believe it is. Wait, let me quickly check my periodic table, for which I've just dropped multiple batteries, that are on my desk, so I hope that serves as some comedic relief right here, because I have my old chemistry book, and this includes a fold-out periodic table. Yeah, argon is heavier than nitrogen 2, N2. Yeah, argon is heavier than N2. So if anything, we would expect N2 to be above argon, which I believe it. Well, I mean, atmospheric layering isn't really a thing until like the first couple of kilometers are passed, because in the lower couple of kilometers gas doesn't mix because there's a lot gas mixes very well because there's a lot of friction due to this Earth's surface and things like that. But that's I guess I'm blowing this point over proportion. Hydrogen is not a noble gas, and according to you, it shouldn't even be on the top because it has a higher charge to mass ratio than oxygen, so it should be at the very top, bottom. Goddamn.
elevations and collect in layers above. This has not been verified by anyone I know, so at this point I cannot say if this is true or not.
Hey!
Through
Credit where credit's due. This is called intellectual honesty, and it's a very, very rare occurrence within the flat Earth thing. He's saying that he doesn't know, and no one has proven that to him yet, or shown that to him yet, so he's unsure. That's credit where credit's due. That's a fine, fine thing you just said there.
With this induction, some pretty amazing things happen when large electric potential differences are applied to gases.
Yes, the
When gases are
ionize, for example. Not only for example, that's pretty much everything that happens. Gases ionize quickly. Or like the air that the charged particles move through is being ionized then, and the conductivity increases by a significant amount.
Placed into an area with a strong electric potential
air around,
difference, we get the phenomenon known as ionic wind.
Oh, well, there it is. Okay.
If a person were to charge themselves up with 1 million volts of static electricity, they could blow out a candle.
Not necessarily 1 million. You can do a lot lower and still be nice.
Almost 2 feet away from the gases rushing away from their fingertip because of the exceptional potential difference.
The potential difference is so high that, as he explained that somewhat passively, the charges moving away from your body essentially move the air around it with it. However, that's not what I would call a continuous force. Yeah.
So that when a gas loses its electric potential, it slows down so much that it turns into a liquid. Like
No. When a gas loses its electric potential, no. The state of matter, right? Whether it's a solid, a liquid, a gas, a plasma, some include some others, depends very much on thermodynamical factors. And if a gas condensates, it gives off energy, right? Because condensation, in order to boil water, right, you need to put energy in, right? You boil water, you put energy in, and the liquid turns to gas. Conversely, when the gas turns back into liquid, it gives off a bit of energy, and this bit of energy is usually invested into the surface tension of the water, right? At least for water droplets, I know that that's the case. So when water forms on your mirror, the energy that the gas had, because it clearly had higher energy, because it was moving a lot quicker than the liquid is being invested in surface tension, and that's what makes it back to a gas. You need a sufficiently cool and let's say condensation-friendly surface. There are some surface properties involved that I'm not going to go into, and also I don't know them by heart. But that's essentially what's going on. It has extremely little to do with any kind of electrostatic force. It even says it in your video, my man. Cold object plus warm moist air equals
window when it's cold outside. The gases hit the cold window and transfer their potential energy to it.
I mean, yes, potential energy, not potential electrical energy. I mean, not really potential energy. That's mostly kinetic, since temperature is directly proportional to the kinetic energy of a part of gas. So you're wrong twice, I believe, within your own explanation and outside of it.
Trying to mediate the temperature. In doing so,
I love how he kind of folds together the whole electronics thing and temperature. And I'm afraid that's where we're going to have to leave it for today. Because those were 17 minutes, 18 again. Ah, God. Thank you very much for watching. I do appreciate you watching. Leave a like if you feel so inclined, and maybe even consider possibly subscribing. With that, I thank you so much for watching, and I'll see you in the next part. Bye!